I'm going to talk a little bit about VSEPR theory, specifically VSEPR theory applied to molecules and polyatomic ions that follow the octet rule. So, the VSEPR theory stands for valence shell electron pair repulsion theory. So this theory helps us to predict the three-dimensional shape of molecules. That way we can understand how those molecules interact with one another and something about their physical properties. So in this theory, as the name kind of hints, it focuses on electron pairs and how they interact with one another. And since they are all composed of negatively charged things, of course, they repulse each other. Now, we can refer to them as electron pairs, we can refer to them as electron groups or electron domains. On here, I've got it listed as electron domains, but I may also refer to it as electron groups or electron pairs. And when I use that terminology, electron domains or electron groups, I'm actually talking about one of 5 possible things, okay? And you can have multiple of them in a particular molecule or polyatomic ion. And those 5 things are lone pairs, single bonds, double bonds, triple bonds, and even single electrons if you had a radical, okay? So all 5 of those things count as an electron domain. So a lone pair is an electron domain. So if you had 2 lone pairs on something, it's got 2 electron domains. The single bond, each individual single bond is an electron domain, but you have to be careful. Double bonds, even though that's 2 pairs of electrons, it's all connected to the same things. And so a double bond altogether is 1 electron domain. A triple bond, same thing, even though it's 6 electrons, it's all attached to the same stuff, it's all in the same area, it's kind of stuck there. So that's 1 electron domain, and so would be a single electron in a radical. Now, what you do when you apply valence shell electron pair repulsion theory or VSEPR theory is you have to be focused on some central atom, and then you count how many electron domains are on that central atom. And then that helps you predict what we would call the parent structure, okay? Which also sometimes we call it the electron geometry, okay? Or some people call it electron group geometry, electron domain geometry. I'll try to stick with parent structure, but I do tend to call it electron geometry as well. So be aware that that's what that is talking about. And so this is just telling you the actual geometry or arrangement of the electron domains. So it's just telling you how they're oriented with respect to another, okay, around some central atom. So if you have a larger molecule that has multiple central atoms, you can apply VSEPR theory, but you have to focus on one central atom at a time and understand how the attachments off of it are arranged, and then go to the next one, think about how those are arranged, then you'd have to piece all that together. And so we'll focus mainly on just having one central atom and applying this theory, but you can build and use it for larger molecules. Now, what this tells us, or what the theory tells us, is that these electron groups, since they're repelling each other, what they're going to do is they're all going to repel each other pretty much with the same strength. Although you can have slight differences in how much one group repels another, in general, you initially kind of assume that they all have kind of the same force pushing away at everything else. So what happens is those electron domains are going to arrange so that they have the maximum amount of space. Okay, they're going to space out to where they're separated the most. That's going to yield a low energy structure, okay? Because those repulsions aren't favorable. They want to get away from one another. And so the further away they can get from one another, the lower the energy of that system. So since we're going to focus on octet rule only, we only have 3 parent structures we need to worry about. Now there is more if you're dealing with exceptions to the octet rule, specifically expanded octets, then you've got some more parent structures, but we're not going to look at those at all. We'll stick with just octet rule. And so if we have things that follow the octet rule, the most electron domains that can be attached to an atom is 4. Okay, so you can have 4 because every electron domain is going to be 2 electrons, or possibly if you have a single, but then you max out at 7 electrons if you have a single electron on that thing. And so at most you have 4 groups. And so we have 3 different parent geometries that apply to octet structures. And that's going to consist of either having 2 electron domains coming off of something, 3 or 4. Okay, and if there's 2, then those things, to get as far away from one another as possible, will go 180 degrees from one another. And so they form a linear structure. So you have some central atom, you have 2 things coming off of it. The furthest away they can get from one another is to be completely opposite sides. So that's 180 degrees from one another. And so that's our first parent structure. That's anytime you have 2 electron domains attached to some central atom. The next one, if you have 3 things attached, then the furthest they can get from one another is to stay in a flat plane, but be 120 degrees from one another. And so what we call that is trigonal planar. Okay, so you have 3 objects coming off of this central atom, and they're all 120 degrees from one another. And that is a trigonal planar electron geometry or parent structure. And then the last one, that's when we actually jump into something being 3-dimensional and not really flat. And that would be a tetrahedral structure when you have 4 attachments or 4 electron groups on something. And what that is everything kind of angles out at 109.5 degrees from one another. And if you were to put, say, like walls on each side of that object, you would create what's called a tetrahedron in geometry. So that 3-dimensional shape, a tetrahedron. And the atoms, those outer atoms, actually are on each point of the tetrahedron. You can also think of it as if you had a cube, they're kind of on opposite corners of that cube, but I think that's harder to picture. And so we've got those 3 parent geometries, and you've got to know those. So you've got to first be able to draw a Lewis structure. Once you have your Lewis structure, you look at the central atom, you count how many electron groups there are. Do not double count a double bond. Don't triple count a triple bond. Each of those things only counts 1 time. And then that tells you how many electron groups, and you should have 2, 3, or 4 if you have some structure that follows the octet rule. And then it means it's one of these 3 parent structures. Now, once you have that, that's really telling us about the groupings of electrons coming off of the central atom. But that's not always what we're interested in. So usually we would take that shape and we would convert it to what we call a molecular shape or molecular geometry. Okay, so that description that we're using for the electron domains that we call either an electron geometry or parent structure, that tells us about the orientation of all those electron groups. But most often we're more interested in just the actual atoms coming off. Okay, and so the molecular shape or molecular geometry is telling us just about the arrangement of the atoms. So if there's lone pairs or lone electrons, they do actually affect the arrangement of those atoms because they take up space and are pushing things away, but they're not part of the description of the shape of the molecule. So the molecular shape is focused on what kind of shape is created by the atoms. Okay, so let's go through if we have our three parent structures, what variations we could have. So our first parent structure was a linear structure, right? And so we can have some central atom and two electron groups coming off. Now, if those two electron groups are attached to atoms, hopefully it's obvious it's linear. Okay, so the parent structure is linear, the molecular geometry is the same. Okay, if everything's, if all those electron groups are actually attached to an atom, meaning if they're all bonds, single, double, or triple, then the parent structure and the molecular shape are the same thing. Okay, now with linear, I don't have any other pictures, but if you thought about in this particular structure, we got BeCl2. If I took off one of those chlorines and exchanged it for a lone pair, I would still have two electron groups coming off of that beryllium, but then I'd be down to just two atoms. Well, and that, the only way we can describe it is still linear. Okay, so it wouldn't change. So a linear structure is just always linear with respect to the parent structure and molecular shape. So that one's not any more complicated, but the other two have some variations. So if we have three electron groups, then remember they arrange themselves 120 degrees from one another, forming a trigonal planar structure. Now, if every single one of those electron groups is some sort of bond attached to an atom, then the molecular shape is still trigonal planar, because that does describe the shape of the atoms. But if we took off one of those atoms, so in this BF3 molecule, if I took off one of the fluorines and exchanged it for a lone pair instead, then what I would have left is what we call a bent arrangement, okay, or bent molecular shape, bent molecular geometry. Some people will call it angular. I'll stick with bent. That is the most common, I think, for that. That's at least all of the intro books usually and Gen Chem books, and so we'll stick with that. And so with that structure, it still has a parent structure of trigonal planar. Okay, so if there's a lone pair and then two bonds attached, then it's still trigonal planar parent, but the molecular shape, the description of the atoms would be bent. Okay, because you think of the lone pair as being invisible. And so the lone pair is not shown on this particular molecule, but basically we have a pair of electrons here. So sometimes people will draw it as a little electron cloud coming off. So that electron cloud there, it's pushing those bonds away from it and causing that bent arrangement. Now with that, this is where you start seeing a little difference in the repulsion of these different groups. So really, a lone pair actually pushes things away more than a bonding pair, so more than a single bond or a double bond or a triple bond. And so lone pairs, they're really only stabilized by one atom because they're only attached to one thing, right? So what happens is those electrons aren't getting as much interaction with positive nuclei, so they end up spreading out more. They're not held onto as well, which means then they are repelling even further other things. Whereas when it's a bond, there's two positive nuclei kind of interacting with those electrons, so it kind of reins them in, and they don't take up as much space, they don't push things away as much. So that's why on this picture, this bent structure, it tells you that the bond angle is less than 120, okay, because that lone pair is actually pushing a little bit harder than those bonds are, and so it's kind of distorting that structure a little bit. Now you can look up exact angles for structures based on, different experiments and calculations, but we're not concerned with exact angles. You should know that if you have a parent structure that's linear, your angle's 180. If you have a parent structure that is trigonal planar, your basic angle is 120. But if you have a lone pair on the central atom, it does distort it some, so it makes that angle a little bit smaller. But you don't have to know how much smaller. That depends on what actual atoms it's made up of. Okay, now let's go through our third parent structure. Okay, we'll go through the tetrahedral structure. So if you have 4 electron domains attached, if all of those things are attached to actual atoms, meaning if they're all bonding pairs of electrons, then not only is the parent structure tetrahedral, but so is the molecular shape. Okay, and it still has bond angles of 109.5. That's your tetrahedral angle. And then if we were to take one of those atoms off and replace it with a lone pair, we'd still have 4 electron groups, so it would still be a parent structure of tetrahedral, but you would now have an arrangement of atoms that is trigonal pyramidal. Okay, and so you still have this lone pair. It's not shown on this, but I can kind of draw in a little lone pair there. So you have a lone pair. It's still taking up space and pushing those other things away. And so what it causes is the shape of that molecule to then be trigonal pyramidal. And so where that name comes from, it's just a geometric type name. So you have kind of a pyramid that is formed with a triangle base. And so that's where that name is coming from. And what you see here is, again, an angle that they say less than. So it's still the tetrahedral angle because it's still a tetrahedral parent structure. But that lone pair, remember, is going to push a little bit harder on those bonds. And so it causes that angle to be a little bit smaller. And then we have one more important structure with tetrahedral, and that would be when we're down to only 2 bonded pairs. And so in this structure, I label it as still tetrahedral. That means there's actually 2 lone pairs on this. It's just not shown in this diagram because, you know, we're focused on the atoms. But if we draw them on there, I have 4 electron groups, 2 lone pairs, 2 bonding pairs. So it's a tetrahedral parent structure. But now if I just focus in on the atoms and describe what they look like, this would be another bent shape. Okay, so the molecular shape is called bent. So there's actually 2 ways you can get the molecular shape bent. That's when you have a trigonal planar structure that has 1 lone pair versus when you have tetrahedral that has 2. But in this case, the bond angle is less than 109.5 instead of less than 120 like it is for a trigonal planar parent structure with a lone pair. Okay, so that's all of your shapes, your parent structures and shapes. You've got to be familiar with those. Now, I had the one table with the parent structures. There's another table here that gives you the parent structure and your molecular shape. Okay, so here we've got our parent structure of linear, trigonal planar, and tetrahedral. So those are all the ones that apply to things that follow the octet rule. Okay, and then the molecular shapes are listed individually below those. Okay, the different possibilities that we can have. And that's all based on, well, how many electron domains, right? The number of electron domains, oh, sorry. Here we go. The number of electron domains, that links to the parent structure. So for linear, it's always 2. And for trigonal planar, it's always 3, right? For tetrahedral, it's always 4. And then they've got here the number of bonded atoms and then the number of unshared pairs, okay? So the number of bonded atoms, if that is equal to your number of electron domains, then your molecular shape is the same as the parent. So here, this one, it's 3 equals 3. They're the same number of bonded atoms and the number of electron domains, so it's the same thing, okay? It's the same name for the molecular shape when you have the same number of bonded atoms as electron domains, meaning everything is attached to an atom. There's nothing that's just standalone electrons. But when you have some unshared pairs, so some lone pairs, on that structure, or possibly a radical, then your molecular shape is something different, and it's describing just the atoms. Okay, so at first it can be helpful to use these tables and look things up. In general, after you look them up so many times, you start to get a feel for it and you just know them. But at first, get the hang of using the tables. That can be helpful. And they even give you some examples in this table. You can draw the Lewis structures of them and see how it matches up with this information. Now I've got some examples where I'm giving you the Lewis structure. Now you should be able to draw a Lewis structure. So if I hadn't given the Lewis structure, you should be able to first draw the Lewis structure, then apply VSEPR theory to answer these questions. Okay, so here I say what's the parent structure and the molecular shape of HCN, and then I want to know also the bond angles. Okay, so I want the parent structure. Well, the parent structure is based on how many electron domains are on that central atom. So carbon's my central atom, and I have a single bond and a triple bond. So I have 2 electron domains, and so that means my parent structure is linear. Okay, and then my shape then, well, both of those things are attached to actual atoms, right? The single bond is attached to a hydrogen, the triple bond is attached to a nitrogen. So those are things I'm interested in seeing, okay? And so my shape is still linear, okay? And then what are the bond angles? Well, the linear bond angle is always 180 degrees, okay? And so it's a straight line. Okay, now let's do another one. Now here we've got PF3, and I've got, again, the Lewis structure. We want the parent structure first, and so the parent we base on how many electron domains we have. So I've got a single bond, I've got another single bond, another one, and then a lone pair on the phosphorus. So you're always focused on the central atom, and then you count how many things are attached. And if there's more than one central atom, you do this for each individual one. So each individual central atom has a parent structure, a molecular shape, and bond angles. Okay. And then if you want to know about all of it together, you have to put that information together. And so that's a little trickier. But here we've got 4 electron domains. So that would be a tetrahedral structure. Okay, and then one of those things is a lone pair. So one of those things we want to kind of ignore. It's invisible, right? So in this tetrahedral structure, if only 3 of those things are visible, then what we end up getting is a trigonal pyramidal structure. Oops. And then this, remember, it's a tetrahedral structure, so the bond angles, the core bond angle is 109.5, but since we have that lone pair pushes a little harder on everything else, so it actually makes it a little bit less than that. Okay, let's look at another one, and let's see. Here I've got what is the parent structure and molecular shape of NH4 plus, and again the bond angles. So I've got the Lewis structure. So if I want the parent, I need to identify my electron domains. I have a single bond, a single bond, a single bond, and a single bond. Right? So I have 4 things attached. So this one again is going to be a tetrahedral structure. And then I want the shape, and every single one of those electron domains is attached to an atom, okay? So all of them are visible, so your shape is the same thing. So it's also tetrahedral. And then the bond angles are going to be, well, the tetrahedral bond angle, so 109.5 degrees. And there's no lone pairs distorting that. So it's just 109.5. Okay, next. We've got carbonate ion, so CO3 2-. Now this one actually has resonance structures, but it doesn't matter. The nice thing about VSEPR theory is you can use any valid Lewis structure. So even if there's resonance structures, you just need one of them, okay? And or even if there's a possible more stable structure, as long as you have a valid structure, so something that has the right number of electrons and follows the octet rule, then you can go with that and use it to predict the shape. Okay, it doesn't have to be the best structure and it doesn't have to be every resonance structure. Okay, so now we want the parent again to start. And so I have a double bond, a single bond, and another single bond. So there's 3 attachments. So that always is a trigonal planar parent structure. And then we want our shape, and the shape is going to be the same because all of those are attached to atoms. So it's also trigonal planar. And then our bond angles, well, it's trigonal planar and it's purely trigonal planar. So our bond angle is just the regular trigonal planar angle, which is 120 degrees. Okay. Okay. On to the next one. Now I've got SO2. And so again, we're going to start with parent. And so we've got a double bond, we've got a lone pair, and a single bond. And so that's 3 attachments. So 3 attachments is trigonal planar. And then our molecular shape, well, we have 1 lone pair. So one of those things we're not looking at, okay? And so you have this trigonal planar structure. Got some central atom attached to 3 things, 120 degrees apart. And so if I erase one of those, then what I have left is a bent structure, okay? And it's a trigonal planar structure, okay, trigonal planar parent, so the angle has to be based on the trigonal planar angle, which is 120, but that lone pair on there is making it somewhat less, okay. Okay, next, here we've got BH3, okay, so we want the parent, and we've got a single bond, a single bond, a single bond. Okay, so we have 3 attachments, and so this one's trigonal planar. And then, let's see, the shape. Well, it's 3 attachments on both of those, or it's 3 attachments, all of them attached to atoms, so it's again trigonal planar. Okay, and if it's trigonal planar, then we have bond angles of 120 degrees. Okay, let's see. Now we've got Br3 plus, and that one, central atom, got a single bond, a lone pair, a single bond, and a lone pair. Okay, so again, make sure you're just focused on the central atom because you want to know how things are arranged about that central atom. So I've got 4 things attached. That means my parent must be tetrahedral. And then my shape, it's going to be different because we have lone pairs on this. And so you've got 2 lone pairs on a tetrahedral structure. So if you're just left with 2 attachments on this tetrahedral structure, it's going to be a bent structure, okay? And then my bond angle needs to be related to the tetrahedral angle because that's what my parent is. And so my core angle is 109.5, but since there's lone pairs involved, it makes it less than that. Okay, and I think, yeah, I thought that might be my last one. That's my last one. So hopefully that gives you an idea of how to apply this. Really, you just need to make sure you know how to count how many electron groups are in a structure, and then you've got to know your 3 parent structures. the angles associated with them, and then how you would describe the remaining atoms if some of those pieces were lone pairs instead. And that's it.